So now I want to do the following example. I want to graph f of x equals 1 over 3 to the x power. And then we're going to talk about the domain, the range, the horizontal asymptote as we proceed in this calculation. We already know that the domain, since this is an exponential, is from negative infinity to infinity. You might be asking me, David, how do we know it's an exponential? Remember, the key criteria for it to be an exponential is that the base that is being raised to the exponent x is positive. And you can see that 1/3 is positive. Okay, so we know that we have an exponential. We know that the domain is negative infinity to infinity. We don't know what the range is, and we don't know what the horizontal asymptote is. Okay? Okay. And we don't know what the graph looks like. But we're going to find out right now. Okay? So let's look at that together. Okay. Okay. So first I'm going to put my x's. Here I'm going to put my, let's say, f of x equals 1 over 3 to the x power. Okay. 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 So you might think to yourself, what x values are we going to use to graph this? Now, for reasons that are probably going to be only too obvious now, I already have a set of points in mind that I'm going to use to graph this, and you will see that I've chosen them to make our calculations as easy as possible. So 0, 1, 2, negative 1, and negative 2. Okay. This will allow us to begin thinking about what the graph is going to look like and how it's going to behave. Okay. So without further ado, let's begin. So first of all, at x equals 0, what it will be 1/3 raised to the 0 power. See, so at x equals 0, my f of 0 is going to be 1/3 raised to the 0 power. But I know that I have an exponential rule that says that if x is not 0, then x to the 0 is equal to 1. So this is nothing but 1. Okay? So I can notate that here in my table, like this. What about at x equals 1? At x equals 1, f of 1 is going to equal, what's my expression for f? F takes an input x and outputs the value 1/3 raised to the x power. In this case, the x is 1, so it'll be 1/3 raised to the 1 power. We know again, there's an exponential rule. It says that if I have a base x that's not equal to 0 and I raise it to the 1 power, well, actually in this case, 0 raised to the 1 power would also be itself, but in this case, it'll just be x. So if I have x to the 1 power, it's always x. Okay, so here, if I have 1/3 raised to the 1, that's just 1/3. Okay. So I know that the value here is 1/3. What about f of 2? Right? If x is 2, then the f of 2 is going to be, so the f of 2 is going to be, f evaluated at 2 is going to be 1 over 3 raised to the 2 power. So it's going to be 1 over 3 raised to the 2 power, or in other words, 1 over 3 squared. What does that mean? That means we're going to have 2 copies of 1/3 being multiplied together, right? So I'm going to have 1/3 times 1/3. Aha, that's very interesting. What happens if I do 1/3 times 1/3? How do I multiply two fractions? I multiply two fractions by basically multiplying the numerators to get the numerator of the product and multiplying the denominators to get the denominator of the product. So in this case, 1 times 1 is 1, 3 times 3 is 9, so it's 1 over 9. Okay. Now what about these over here? Let's look at these together. Okay. So over here, okay, I want to calculate the f of negative 1. So the f evaluated at negative 1, where the x, in other words, I want to find out the function value when x is negative 1, right? So the f of negative 1 is going to be 1/3 to the negative 1 power, right? Now Now you might say to me, well, David, based on, we know the following fact. We know that x to the negative n is equal to 1 over x to the positive n, right? We know this fact, right? So then here, this can be written as 1 over 1/3 to the first power, right? Right, if I have 1/3 to the negative 1 power, then that's the same thing as 1 divided by 1/3 to the 1 power. Now what is 1/3 to the power 1? It's just 1/3, right? I know that x to the 1 power is equal to just itself, x. So here I get 1 divided by just 1/3. So now we ask ourselves, we have 1 being divided by a fraction. What happens when we divide by a fraction? We multiply by the reciprocal. So in this case, I'm going to have the numerator, the 1, times the reciprocal of the denominator. What's the reciprocal of 1/3? 3 over 1. Now here, what's 1 times the number? 1 times the number is whatever that number is. 1 times a for any number is a. 1 times 2 is 2. 1 times 3 is 3. 1 times 3 over 1 will be 3 over 1, right? By the same reason. And of course, the fraction 3 over 1 corresponds to just the number 3. Okay. Okay. So this one is 3. Okay. You're like, wow, awesome. Okay. Okay. And now finally we're going to calculate what's the value of f of x as x is negative 2. By the way, I know I'm going into extreme detail there, but it's just that I want to make sure you guys can see how to calculate these values. Okay, and what rules I'm following as I do these calculations. Because that way you guys will be able to do the calculations also. And so now we want to calculate the f evaluated at negative 2. So I'm going to have f of negative 2 is going to equal to 1/3 raised to the negative 2 power, right? Now again, we know that this is going to equal 1 over 1/3 to the square power. Why? Because we know that x to the negative n is equal to 1 over x to the positive n. Okay. Then we know that this is going to equal to 1 over 9. Now, how do I know that? We saw earlier when we were calculating f evaluated at 2, which is 1 over 3 to the 2 power, we saw that that gave us 1 over 9. Or alternatively, we could calculate it ab ovo. Okay? So in other words, like in case you want to like sound smart, you could say ab ovo to mean from the beginning. It's Latin. You'll see it in some math books. Okay? But that's what it means. It means from the beginning. Okay? Okay. No, but okay, all joking aside, I just threw that in there as a joke. Yeah. We can calculate it from the beginning as follows. If we have 1 over 3 squared, right? What is that? We're going to have 2 copies of 1/3 being multiplied together. So that's going to be 1/3 times 1/3, like this. And then, of course, again, how do we get the product of 2 fractions? The product of 2 fractions is the fraction whose numerator is the product of the numerators of the fractions being multiplied. In this case, 1 times 1. And whose denominator is the product of the denominators of the fractions being multiplied. In this case, 3 times 3, which is 9. Right? And so that's how I got that. Okay. And then I know that here I'm running into a different problem. What is the problem? I have the number 1 on top being divided by a fraction. What happens when we divide by a fraction? We multiply it by the reciprocal. Okay, so in this case, I'm going to have the 1 times the reciprocal of the bottom. What's the reciprocal of 1 over 9? 9 over 1, like this. And then here I have 1 times 9 over 1. Well, we know that 1 times any number is that number. So 1 times a is a, 1 times 2 is 2, etc., etc., etc. Here, 1 times 9 over 1 is 9 over 1. And then we look at this fraction, 9 over 1, we ask ourselves, what is it? Ah, okay, it's just 9. Right? Because the fraction whose denominator is 1 is equal to the numerator. Okay? So here, 9. And now, from this, we can start to see some of the behavior of this function. Okay? We're kind of beginning to speculate in our brains from this table, right, that as the x is increasing, the f of x is decreasing, right? And as the x is going more negative, this way, more negative, the f of x, the y values, the f of x is going bigger and bigger, okay? Now we might ask ourselves, why is that, right? Let me make a brief discussion here before we move forward, okay? Because this is going to be super important. Okay, I want to make an observation here that is going to be important for us. So I want to ask myself, I want to look at f of x. Our f of x here is 1 over 3 to the x power, okay? Right? Okay, I'm sorry, but I need to make a segue here. Right, we saw the trend in the table, and we kind of look at this trend and we can see that it's kind of operating reverse to what the first example was, right? The first example, as we were going in increasing x, the y's were increasing, and as we went in decreasing x, the y's were decreasing. And here we see the opposite trend occurring. And so what I'm about to show you is, I want to try to make a connection in that case so that you guys can see it also, okay? And also I want to use the algebraic identities that we saw earlier to recast this example in a different light that will both enable us to appreciate that opposite behavior that we see in the table, as well as to use what we saw before to help us draw some conclusions, okay? And then we'll of course look at some verification, okay? Okay, but so anyway, in this case, so we're looking at this 1 over 3x, and we ask ourselves, what can we see here? So we might say, aha, well, if I had x to the negative n is equal to 1 over x to the positive n, then because I know that 3 to the 1 is equal to 3, maybe I can say, aha, 1 over 3 is the same thing as 1 over 3 to the 1 power, right? 1 over 3 to the 1 power. Maybe, is that 3 to the negative 1 power, right? Well, the answer to that is yes, right? So I can see this f of x as 3 to the negative 1 power raised to the x. Okay. That's very interesting now. And we know that if we have x to the nth power raised to the mth power, then this is x to the n times m power. So if I have 3 to the negative 1 raised to the x power, then that's the same thing as 3 to the negative x power. Okay? So what I've just shown you here algebraically is that the f of x that we originally wrote down, right, can also be written as 3 to the negative x power, okay? And we know that, and so let me write that down here, and I'm going to make a quick discussion here about that. It's very important, right? So I have f of x is equal to 1 over 3x, or equivalently 3 to the negative x. Now, if you use these same x values with 3 to the x, okay, let's pretend I have a table here. Let's pretend there's going to be x, and g of x is going to equal to 3 to the x power, okay? In other words, it's going to be very similar to our previous example, but with the 3 instead of the 2. Then you'll be able to see that the values, if you plug them in, are going to be like this. Okay, if you have 3 raised to the x power, you get that table. And you can do that just like, you can do the calculations just like we did in the previous example with 2 to the x. But now I'm going to make my point here. If g of x, so here in the side I've written it as g of x is equal to 3 to the x power. And of course we can see that that table has the same kind of behavior that our 2 to the x table had. That is, as x goes off to the positive infinity, as x gets larger, the y values get larger, and as x goes to negative infinity, as the x values get smaller, the y values also get smaller. But we saw in that case, as x goes more and more negative, the y values get closer and closer to 0, but never touch 0, right? Now, from our transformation videos, we know that if, let's say, g of x is a function then if I can write the function f of x as g of negative x, then f of x is a reflection of g of x across the y-axis. Okay? So this is a fact from transformations. And we remember that, what does that mean? Okay, that means the following. If I draw my, well, let me show you here. Let me draw the picture so you guys can see it. So in this picture, I'm going to draw my g of x here, which is 3 to the x power. Not 3 to the negative x, 3 to the x power. And we can see from this table, and in comparison with our example from before, the y equals 2 to the x that we graphed in the previous video, we can see that it's going to look like this. Okay? Right? And of course, if you plot it on graph paper with listing the points out, you can draw a better graph than this. But you can see that this has all the trends. We know that at x equals 0, it crosses at 1 in this case. As x increases, the g of x increases. We know that, like, for example, at x equals 1, the y value will be 3. At x equals 2, the y value will be 9. And over here, same thing. And we know that the horizontal asymptote will be the x-axis, or in other words, the value y equals 0, because as we can see, 3 to the x, as x becomes more and more negative, will be 1 over 3 to an increasingly positive number, which will be a positive number that's getting smaller and smaller. So in other words, it's going to get close to 0. Horizontal asymptote, y equals 0. So in this case, we know that the domain will be negative infinity to infinity. The range of the 3 to the x will be from 0 to infinity, not including the 0. The same argument that I just gave, same argument I gave in the previous video. And we know that the horizontal asymptote, the HA, will be y equals 0. Again, same reasoning as I gave above. It's going to get closer and closer to 0 forever in this direction. But from this fact, we know that I can write, look at what f of x is. Or look at how I can see f of x. If g of x is 3 to the x, then I can see that, what is f of x? F of x is 3 to the negative x. What is that? That's the same thing as, let me do it differently. Because if I do it this way, you'll see it. If I take g of negative x, okay, my g of x is 3 to the x. If I take g evaluated at negative x, it'll be 3 to the negative x. But what is that? That's exactly my f of x. So what I've shown here is that I can write my f of x as g to the negative x. That is to say that in this case, our g of x is 3 to the x. And I've written f of x now in terms of, I've written f of x now as g of negative x. And so f, this original function of interest to us, is the reflection of g of x, the 3 to the x, across the y-axis. What does that mean? That means that if I take this as a sheet of paper and I flip it upside down, not upside down, but if I flip it like this, then I'm going to get the reflection across the y-axis. And so that means that our graph of this function is going to look like this. Now, so this is my f of x. Okay. Now, we can see that this graph over there on the right-hand side bears out the pattern we see here. As we go increasing negative, the graph is increasing like this. As we go increasing positive, the graph is asymptoting to 0. And that makes perfect sense because it's the reflection across the y-axis of the original function g of x. But let us think for a moment. If we reflect across the x-axis, the x values of the points switch from positive to negative and vice versa, but the y values don't. So if the range in the original case goes from 0 to infinity, then when I reflect it, for all the points of the graph, only the x's switched from positive to negative, or vice versa. So all the y stayed the same. Since there was no points in the original graph that had y 0 or less than 0, there will be no points in the reflection that have y value 0 or negative or less than 0. And so the range of this function is going to also be 0 to infinity. Also, the reflection across the y-axis does not change the location of the horizontal asymptote. And of course, we can see that if we pursue the same kind of argument we did for the last problem, we can see that as we increase the x, we're going to get a fraction 1 over. In fact, I'll do that argument right now in a moment so you can see that with your own eyes, but we can see that the horizontal asymptote will also be the same. In this case, y equals 0. We can argue it along these lines via the transformation, or we can argue it using the argument I'm about to give you real quickly. But anyway, I wanted to make this quick segue before we actually do the before we actually drew this graph carefully, that we can see this as a transformation, and that can help us glean insight from our previous example and attach it to this example. Okay. Anyway, I know that this was a super long segue, but so let's go back to drawing the graph as is, or using our table of points and stuff. Well, actually, before we do that, I want to make a quick discussion of why it makes sense that we're going to have a horizontal asymptote of y equals 0 again in this case. And so let's do that together. Okay? So we saw that we could see that from the previous case, where if we reflected across the y-axis, then obviously the horizontal line y equals 0 gets mapped onto itself, right? And we saw that all the points that would have been getting close to y equals 0 on the left in the original graph would be getting close to y equals 0 on the right hand side. So from a geometric perspective, we can see the fact that we could identify this as the reflection of 3 to the x across the y-axis gave us very good cause to believe that the horizontal asymptote of this one would also be y to the y equals 0, or in other words, the x-axis. But here we're going to look at it kind of from a different perspective, because we want to find out what's going to happen as x gets larger and larger, right? We can see that the trend here is that the y values, the function values, are decreasing, and it's natural to ask, will the y values decrease to the point that they eventually become negative, or that they at least become 0 at some point? And so let's look at this together. So I have f of x is equal to 1 over 3 to the x power. I want to imagine now, we already know that f of 1 is 1/3. We know that f of 2 is 1 over 9. Okay? We know that, but what is f to the 100, for example? What is that? That's going to be 1 over 3 to the 100th power. Okay? So I'm going to have 1 over 3 times 1 over 3 times times 1 over 3 with 100 copies of 1/3. Okay. Just to make this example look artificially more complicated, I could have evaluated f to the 1 million, which would have been 1/3 to the 1 millionth power, and I would have 1,000,000 copies of 1/3 being multiplied. But I felt that that was just too comic for us to approach, and it would have not served our purposes. But in any case, you can see here, I have a positive times a positive, which will be a positive, times another positive will be a positive, times another positive will be a positive, all the way down. So I'm going to end up with a positive number, right? But on the other hand, I do know that if I do that, I'm going to have 1 times 1 times 1 times 1 100 times. Well, 1 times 1 is 1, and times 1 again will be 1, etc., etc., etc. What about the bottom? 3 times 3, that's 3 squared, times 3 will be 3 cubed. How many of them I have? I have 100. So it's going to be 3 to the 100th power. So we know that the product is going to be positive as we walked along that line. 1/3 times 1/3, positive times a positive is a positive, times 1/3 again is a positive because they're both positive, etc., etc., etc. So we know it's positive. But but look at this denominator. This denominator is 3 to the 100. Now, if you put that in your calculator, it's going to be an overflow error. And of course, I'm not encouraging you to put it in your calculator because, as you can see, we're not really using a calculator here. But if you think about it in your brain, 3 to the 100 is a huge number. So if I take 1 and I divide it by a huge number, that's going to be a very tiny, tiny, tiny number. Okay, very tiny. Okay. And so if I were to calculate f of 1,000, I'm going to still get a tiny number, but it's still going to be positive. And what I want you to see from this trend is that the values are going to be, no matter what the x is, no matter how big the x is, no matter how far along this table I go with x getting bigger, this right-hand side from our argument here will be, we believe, will be positive. Well, not we believe. We know that it'll be positive, number 1. And number 2, it will be increasingly small. Okay? Right, if I were to do f of 101, by the same reason as we did here, it'll be 1 over 3 to the 101. And if you know your calculations with fractions, you know that this will be nothing but 1/3 of 1 over 3 to the 100, which is 1/3 of f of 100. Okay? And what is that? Or what does that mean? That means that every time I increase the x by 1, the height will be 1/3 of what it was before. Okay? So if I can't believe I'm about to show this. I mean, strictly speaking, I shouldn't show this, but I got so tempted now to show it to you that I can't resist it. Okay? If this is my x-axis or a piece of it, okay? Oh my God, I can't believe I'm gonna show you this. And this is, by the way, this squiggly line is just to say that it's chopped off somewhere, and that I'm gonna put the y-axis here as a measuring stick, so to speak. But this means that there's tons of x-axis in between, but I'm cutting to the y-axis so I can look at the y-axis, right? And so if this is some value, some particular value x, and this is some particular value x plus 1, okay, then, and let's say this, okay, let me move this table a little bit so I can have enough room here, so I can make this beautiful discussion, this beautiful side discussion, right? Or at least I hope it's beautiful. But from this discussion, we can see that, if this is let's say f of x, then here will be f of x plus 1. Oops. Oh no. See, and this is the y-axis, right? Let me look at this, and then. And we can see that. Okay, so in other words, what I'm saying here is that if I increase the x by 1, the height of the function at the left will be 3 times that of the function on the right in this particular case. Or another way of looking at it is, as I go from any point x to 1 greater, the height here is 1/3 of the height here. Okay, so in other words, we can see that as the x increases, it is getting smaller. Okay, and again, but of course, it'll never be 0, because no matter how small this is, right? This will still be positive. It'll just be 1/3 of it. Okay. Oh my God. But anyway, that's a little technical point, and I couldn't resist showing that to you. And if it's confusing, I understand. It's kind of But so now we're gonna finally draw the graph. But I couldn't escape the desire to go off that little tangent to see you like how you can look at it, how you can look at the graph with like a magnifying glass. Okay, and but after going off of that very exciting tangent, I wanted us to, well, we're gonna go back to graphing this using the points that we had gotten. And of course, we also already saw that we're fully justified in seeing that the horizontal asymptote is y equals 0, aka the x-axis, and that the range is 0 to infinity, because we saw again that the values as we go as x gets bigger, in this case the 1 over 3x gets smaller, but it never becomes 0 because it's always 1 over some number. In fact, 1 over 3 to the x power for x, large. And so 1 over 3 to the x, 3 to the x is always positive. So 1 over 3 to the x is always positive also. It's just extremely small. And as we go leftwards, it'll end up being 3 to the positive value, okay? Like, for example, 3 to the negative 2 is the same, 1 over 3 in parentheses to the negative 2 power becomes 3 to the positive 2, okay? And so we can see it makes sense that it'll go upwards like this, okay? And in fact, if we follow that like logic that we had a little bit earlier, if we go to the left by 1, whatever the height was at the right, it'll be 3 times as high on the left. Okay, you can make the same kind of argument I made like a little bit ago, but anyway, we're not going to do that right now. Okay. Couldn't help it, guys. So like here, negative 2 to the 9th power. Negative 2 to the 9th power. My brain's already gone. At x equals negative 2, and the y value is 9. So x equals negative 2, that's here, right? Then I'm going to count up 1, 2, 3, 4, 5, 6, 7, 8, 9. Nah, I'm just kidding. I couldn't help making a deep voice like that, like just to add some excitement to this problem. At x equals negative 1, we have y value 3. X equals negative 1, 1, 2, 3. X equals 0, y value 1. X equals 0, y value 1. Okay. X equals 1, 1/3. And of course, at x equals 2, 1 over 9. So it's going to be like that. We can see here we know that as we go this way, it's going to get closer and closer to the x-axis, to the line y equals 0. And as we go to the left, it's going to increase on forever. And so what we can say here is that this exponential function is decreasing everywhere. It's strictly decreasing. As we move rightwards along the graph, the y values get smaller and smaller, in other words. Let me write that down technically here for us, and let's continue. So now here, just to be technical, if 0 is less than b is less than 1, then b to the x is strictly decreasing. That is, if x1 and x2 are any real numbers, okay, and if x1 is less than x2, right, then the b raised to the x1 will be bigger than the b to the x2. You see, if I take this value if x1 is here on the x-axis, then bx1 is this height. And if I take any value of x2 that is larger, like let's say this one, then you can see that the b to the x2 is smaller than the b to the x1. And so that's what we mean when we say it's decreasing. And it's strictly decreasing because that's true no matter how close together the x's are. The x that's larger will have a shorter height with this function than the bigger one. And we can see that this applies to this case because you can see that in our case our b is 1/3, and 1/3 is between 0 and 1. Okay, we saw that it was different in the case of b equals 2, or in the case of b equals 3, because in that case the b is bigger than 1, and we saw that that was the case of strictly increasing, and this is the case of strictly decreasing. Okay, I hope you've enjoyed this example, and I hope you've also enjoyed this segues, and I look forward to seeing you again soon. Thank you.